Hello students, now we are going to start our 45 problem assignment of electromagnetic induction. First problem is from 1991 AIPMT. A magnetic field of 2 into 10 to the power minus 2 Tesla acts at right angles to a coil of area 100 square centimeter. With 50 turns, the average EMF induced in the coil is 0.1 volt when it is removed from the field in time t. The value of t is, we know that what is E? What is E? If you are removing the coil from the magnetic field, means you are making the flux zero. If n turns are there, what is E? Basically E is, we are talking about magnitude only, they give magnitude, d phi by dt. What is phi? Phi is NBA. So what you make dNBA means change in flux. You make NBA 0 in a time, suppose delta t. We want to calculate this time in which you make this flux 0 by removing the coil from magnetic field. So it should be NBA upon E. What was E? E was 50, no problem. What was B? SI unit 2 into 10 to the power minus 2 Tesla, but take care of A, not in SI unit. So multiply it by 10 to the power minus 4. What is E? E is 0.1. 0.1 means remove this decimal, put 110 there. Now see, how many positive zeros are there? 50 into 200, 20 this and 20 this. 4, they will cancel, minus 4 means 50, 2 and this 100, they will cancel this. Now 10 to the power minus 2 into 10, 10 to the power minus 1 means you done your job in 0.1 second. So we are going with A. So answer of first question was A. Now we will move to second problem. Just I told you in theory slide, Faraday's laws are consequences of conservation of energy. So we are going with A. Next, it is from 1992 AIPMT. A rectangular coil of 20 turns and area of cross section 25 square centimeter has a resistance of 100 ohm. If a magnetic field which is perpendicular to the plane of coil changes at a rate of 1000 Tesla per second, the current in the coil is, what I told you, induced EMF is given by N into d phi by dt. Not talking about direction, only magnitude, because we need only magnitude and they give only this. What is d phi? Phi is B into A. Sometimes B is changing, sometimes A is changing. If B is changing, you will get E. If A is changing, you will get E. In this problem, area was constant. So take it outside. What is remaining? dB by dt means rate of change of magnetic field. And they gave us 1000 Tesla per second. So now we are able to calculate first E, number of turns 20, so it is 20. area 25 square centimeter, means 25 into 10 to the power minus 4. Rate of change of magnetic field 1000 Tesla per second. But we know that E is equals to I into R. So what we are getting? 20 into 25, 500. Two positive 0, 2 positive 0. Cancel this for negative 0. So what is I now? 5 into 10 divided by R. R was 100. So 50 by 100 means, cancel this 0 with this, 5 by 10 means 0.5 ampere. So we are going with option C, 0.5 ampere. Next, it is from 1992 AIPMT. The total charge induced in a conducting loop when it is moved in magnetic field depends on, we know that, what is E? E is minus change in flux upon time in which it occurs. But E is I into R. What is I? Rate of flow of charge, means charge flowing per second. So clearly you can see induced charge depends upon two factors: total change in flux and resistance. Not rate of change of flux, time is cancelled. Not initial magnetic flux, total change in magnetic flux. So we will go with C. Next, it is from 1995 AIPMT. A straight line conductor of length 0.4 meter is moved with a speed of 7 meters per second, perpendicular to a magnetic field of intensity 0.9 Weber per meter square, means Tesla. The induced EMF across the conductor is, we have a derivation in our previous slides, कि if L length conductor in magnetic field B is moving with a speed V, induced EMF should be BLV. Take care of units only. B SI unit 0.9, L SI unit 0.4, V SI unit 7. 9 into 4, 36. Decimal after 2 please, so 0.36. 7 6 are 42, carry 4. 7 3 are 24, 1 and 4, 25. So 2.52 volts, so we will go with option D. Next, it is from 1996 AIPMT. A metal ring is held horizontally and a bar magnet is dropped through the ring with its length along the axis of the ring. The acceleration of the falling magnet is, we have solved this in our theory slides. Okay. If it is coming through the ring, magnet is vertically coming downward, induced EMF will generate in this coil, and cause of that induced EMF to oppose the motion of this magnet, so it cannot come with acceleration g. Due to this opposing force, it will come with acceleration less than g. So we will go with C. Either it is in this position or it is going downward. And every time the role of induced EMF to oppose the motion, when it was upside the ring, it was repelling it. When it was going away from it, it was attracting it. So every time it was less than G. Next, it is from 2004 AIPMT. The magnetic flux through a circuit of resistance R changes by an amount delta phi in a time delta t. Then the total quantity of electric charge that passes any point in the circuit during the time t is represented by, just we have calculated this. In previous slide, just we calculated this, delta phi upon R only. So with which answer we should go? We will go with option B. Next, as a result of change in the magnetic flux linked to the closed loop as shown in the figure, an EMF V volt is induced in the loop. The work done in taking a charge q coulomb 1 along the loop is, induced EMF means potential difference. If charge q is moving and potential difference is V, you know that work done q into V. So we are going with option A. Next, a circular disc. It is from 2008 AIPMT. A circular disc of radius 0.2 meter is placed in a uniform field of induction 1 upon pi Tesla in such a way that its axis makes an angle 60 degree with B. The magnetic flux linked with the disc is, we discussed in our theory part, phi is equals to B dot A. Dot means BA cos theta. Everything is given and given in proper units, so no need to change it. What is B? 1 upon pi. What is the area of a circular disc? Area of circular disc means pi r square. What is r? 0.2. Square means 0.2 into 0.2. What is cos theta? Theta is 60 degrees, so cos 60 is 1 by 2. Cancel pi with pi. 1, 2 with 0.2, you will get 0.1. So what we are getting? 0.02. What is the SI unit? Weber. So we will go with option C. So we got the answer C. Next, it is from 2009 AIPMT. A rectangular, a square, a circular and one elliptical loop. One is rectangular, one figure is square, one is circular and one is elliptical. 4 figures are given. All in the xy plane are moving out of a uniform magnetic field with a constant velocity v into I. The magnetic field along the negative z axis, suppose this paper is xy plane. So magnetic field negative z means inward direction. It is direction of magnetic field. The induced EMF during the passage of these loops out of the field region will not remain constant for which figure they are saying it is not constant. See, I am making this. It is suppose magnetic field or everywhere magnetic field is there. All figures are coming out. I am making magnetic field there, so you will understand better. I am drawing a line. See, in this figure, when it is coming out of here magnetic field, in this region and this region B is not presented. See, in this figure and in this figure, the area which is coming out, it is coming out with a uniform rate, means everywhere area is same. Area is same. But area coming out from this line, dotted line, is not same for this. It is maximum at diameter. It is maximum in major axis. After that, area will decrease. So in these two, the change means induced EMF will remain constant because change is the same. Change in flux is same. But in these two figures, since A is different, so dA by dt will be different for these two figures. That's why in this, E cannot remain constant. So we will go with option A. Next, it is from 2009 AIPMT. A conducting circular loop is placed in a uniform magnetic field of 0.04 Tesla with its plane perpendicular to the magnetic field. The radius of the loop starts shrinking at rate of 2 mm per second. The induced EMF when the radius is 2 cm will be what you know about A. Area is pi r square. And what you know about E, I am writing here. E is magnitude, I am talking only. D phi by dt, and phi is BA. B is constant, take it outside. What is A? A is pi r square. We write there. Pi is again constant, take it outside. So what we are getting, d upon dt of r square. You know a little bit about differentiation. If you differentiate it by chain rule, you will get 2r into dr by dt. Now each and everything is given, and we can calculate E. What is the value of pi? All options are in pi, so we are putting it as it is. What was B? B was 0.04. What was the value of 2? 2 is always 2. What is R? We want to calculate E when R is 2 centimeter. 2 centimeter means 2 upon 100 meter. What is dr by dt? Shrinking at the rate 2 millimeter per second. Dr by dt is 2 millimeter. Milli means 10 to the power minus 3. So we got all things. Now we have to calculate. The numbers are 4 into 2, 8 into 2, 16 into 2, 32. What is the 10 power of 10? Here minus 2. Again minus 2. Minus 4 and minus 3, minus 7. So write 32, 3.2 into 10. Unit is volt. So what we got? We got 3.2 into 10 to the power minus 6 volt. Minus 6 means micro. So we will go with 3.2 microvolt. 3.2, one pi was also there, this pi. Don't forget this pi. Pi is present all times of calculation. It was there, pi was there, pi. So what we will write? 3.2 pi microvolt. So we got option A. Next, it is from 1990 AIPMT. The current in self-inductance is to be increased uniformly from 1 ampere to 11 ampere in 4 milliseconds. Induced EMF is again direct formula. E is equals to L into di by dt. Talking about magnitude only, no minus in 4 options. What is L? 40 millihenry. Remove this milli. Minus 3. Di, change in current, 1 ampere to 11 ampere. 10. It is 10. 11 minus 1. Change in time, 4 milliseconds means 4 into 10 to the power minus 3. Remove minus 3 with minus 3. 4 tens are 40. 10 into 10. What we are getting? 100 volt. So we are going with A. Next, it is from 1991 AIPMT. If the number of turns per unit length of a coil of a solenoid is doubled, the self-inductance of the solenoid will. We discussed in theory slides that induced self-inductance of solenoid is directly proportional to N square. What we are doing? We are doubling the number of turns. So it means L upon N square. It should be constant. Initially, it was L, number of turns were N. We want new self-inductance. Question is oral, you can do oral. And you are making 2n, so it will become 4n square. What you are observing? That L dash will become 4 times of L. So we are going with D option. Now we are going to solve 14th problem from 1993. What is the self-inductance of a coil which produces 5 volt when the current changes from 3 ampere to 2 ampere in 1 millisecond? Problem is very simple. Formula is there. E is equals to L into di by dt. You want to calculate L, so take L on one side. E into dt by di. What EMF you are getting? 5 volt. In which time? 1 millisecond means 10 to the power minus 3 second. What is di? Change in current is 1 ampere. So what we are getting? 5 into 10 to the power minus 3 Henry. Minus 3 means milli. So we will go with 5 millihenry. Means B option is correct. Next. If N is the number of turns in a coil, then the value of self-inductance, we have derivation just before these 15 numericals. I show you that self-inductance is directly proportional to N square. So we are going with C.